But some different stuff today. We're going to add some new features to our table and some new concepts that are useful to us when we're analyzing functions. Okay, this.
Thank you.
Oh.
Representation of my life.
Okay, that's going to look a little different, right, than what stuff you've seen in the past. What's going on with our limit? Oh, this is good stuff. Thank you. No, you never dealt with limits. Okay, what do you suppose this means? Taking a limit as a function as what?
Infinity. There's an infinite amount of limits.
Okay.
You shouldn't do it.
As x approaches infinity, that's a little different. We've always in the past, and I've maybe said this a couple times, but we've never talked about it. We've always taken limits as x approaches a discrete value, right? Infinity is not a number, right? So this is a different thing. This is it's sort of a concept in a way. We want to look, this is what we're looking for the tails of the function. We want to see what happens, in this case, like way out there, right? As x gets big without bound, what does the function do? Okay, what's its behavior? So this just means, and there may not be some describable behavior. Maybe it's just random. In some cases it is, but sometimes it's not. Sometimes a limit exists. If the function approaches a definite value as x gets big without limit, as x approaches infinity, we'd say, then we call that an infinite limit. Okay, let's just take a look at this function real quick, and let's graph it and see what happens. So if we graph the function, there we go. So if we graph the function 3x squared divided by x squared, plus 1, and let's go
Why -4?
I didn't mean to do -4. I'm gonna make the y. I'm gonna change the y values a little bit just so we can see it better. Okay, let's try that. Yeah, that's what it does, right? It looks like it approaches 3. We haven't gone very close to infinity though. We've only gone out in the positive x direction 10, right? Let's make it a bigger number. Let's go out.
Isn't that just as close to infinity as like whatever number you pick?
Well, yeah, I mean you can't ever get close to it, but what I mean is we haven't picked a number that's really far away from the interesting. If we look at the graph here, there's some interesting things happening here, right? It looks like we've got a relative minimum. It looks like maybe we've got a couple inflection points here, right? But then the function kind of gets boring after that. It doesn't look like there's much going on. So if we go far to the right of the area of interest, where we're finding critical numbers, what's going to happen? We're going to see it just gets pretty boring. So how about if we go from -1,000 to positive 1,000? Oops. And it looks pretty much like the line, what?
Flattens out.
Flattens out. What does it seem to be approaching? A y value of
0.
3. Does it seem to be approaching a y value of 3 as I go out here?
Oh, yeah.
1, 2, 3. And I can see that if I go on well, I'll just trace. If I just trace to the right, look what's happening to these values.
They're getting bigger.
And they seem to be pretty much approaching 3, don't they?
But the y will every time to the same.
Bigger.
What's that?
The X
X is
approach.
going in, but not.
Yeah, the x is, right, the x, as
No,
x
that's not-
approaches infinity, as x approaches infinity, the y just seems to approach 3.
Okay.
It's getting there slowly, but it's getting there.
Is
Right.
it ever going to get there?
The answer to that is no, it's not going to.
And we know that because.
Well,
It's like the door,
we
There's a.
know that,
because of that +1, that's why.
okay, we know that because for any value of, well,
I mean, don't.
I guess there's not an easy way to see that, but I promise you it's not going to. Hey, there's too much talking, this is a little distracting, yeah.
Isn't it not, like, it one approach 3, because you always have that +1 on the bottom, that is keeping it from ever being like truly 3.
Yeah, so it's, right, so if it were just, that's a good way to look at it. If it were just like this, it would be 3, wouldn't it? Okay, but the bottom is just a little bit bigger than what it would need to be for it to be 3. As the bottom gets bigger, what happens to the fraction?
It
It's
gets
smaller, right? As x gets huge though, that +1 is gonna get less and less significant, isn't it, right?
Yeah.
And so you can see that it's never quite gonna get there, but it's gonna approach more and more closely. This has the same behavior, and this is something, I'm not gonna go into, I want you gotta read the textbook a little bit. And that's, I need to start to have you do that a little bit more as we get into some new stuff here. Not because I think, well, it is a good textbook, this is a good textbook. But the thing I want you to get used to is kind of reading some of the math notation. And I want you to get used to just, I'm gonna just have you do this on your own. I'm not gonna, I'm not gonna talk an awful lot about, well, I could, but I'm not gonna spend a lot of time with the theoretical, at least for now, with what we call the sigma epsilon definition of a limit. It just, I think it gets too cumbersome. We'll come back at the end of the year and maybe take a quick look at it, but it's not that big a deal. I would much rather you get really comfortable with the idea of the concept of what a limit is. And this is gonna have the same conceptual behavior as the limits we talked about earlier. I'm gonna go back to this old example. Remember what we said, and this, get a lot of mileage out of this. If I were gonna cut my distance to the door in half every second for the period of eternity, assuming that space could be infinitely subdivided, I'll never get to the door, right? But there's also never a place that I could never make a dot on the floor that I wouldn't step on. Does that make sense?
Yeah.
Okay. The same kind of thing is going on here. I'm never gonna get to a y value of 3, right? No matter how long this function goes out to the right or the left, it turns out. But I can always get closer, but I'll just never get there. There's not a single y value less than 3 that I couldn't pick, that I won't eventually cross, right? But I'll just never get to 3.
So would you say like that's the.
So it is, right, so the answer to this then, to this limit is 3, okay? And if we graph this thing, what do you suppose, real quick, if we were just to sketch a graph of this? The graph, we could see it kind of did this, right? It came over and it dipped down, and then it went up, and it kept approaching that value. What do we call a value like that? Yeah, it's an asymptote, isn't it? So if the if the limit of the function as x approaches infinity is 3, then that's telling us that there has to be a horizontal asymptote at y equals 3. Okay, there's a horizontal line there, y equals 3, that the function is going to get closer and closer to. And mathematically, we could say that it kind of sticks to that asymptote, but it just never quite does. Okay? Asymptotes are really useful, though, for us in sketching a function. If we kind of worked backwards on this, if we did the calculus, which we're going to learn how to do, and we found, before we even sketched a graph of this, and we found out that there was a horizontal asymptote at y equals 3, well, we would know that the function at the tails would tend to stick to that asymptote. Now, we don't know yet if the function is above or below the asymptote, or if it crosses the asymptote. We don't know that stuff. But the other calculus that we've learned presumably would allow us to find these other points. We could find the relative minimum, we could find the points of inflection, and from the table that we've developed, we could pretty easily fill in the rest of this, but knowing where that asymptote is, you can see how that's pretty helpful in sketching a graph, right? Okay, so then the question is, how can we get this answer without having to graph it and look at the function, right? Use either graphical or numerical methods. We want to use an analytical method where we get the exact answer without having to, no guesswork, right? So how do we do that? Well, there's a couple things we need to be aware of. I want you to see if you can tell me what the answer to this is. This is a theorem that's in your book, but they in the book talk about this as being for R as a rational number, but it doesn't have to be. Turns out it can be any real number. It doesn't have to be rational. Yes.
This isn't 3.5 of the book?
Yeah, this is the next section, 3.5. Yeah. Okay, so what do you think this is going to be?
Are you writing down the theorem?
Yeah, you're going to fill in the blank. This is the theorem. This is what they call theorem 310, limits at infinity. You'll see this when you do the reading. So if R is some positive real number and C is just an element of the reals, so it's just any real number. Could be anything.
Is that like an arrow?
No, it's
Or is that like
it's
weird
a
E?
it's a sideways
Is it like a sun?
kind of a, I don't know what you'd even call it. It's just an element symbol. It's not. It sort of looks like a rounded E.
Are we?
What does that mean?
What's that?
Are we using math words, right?
Yeah. Yeah, I'm just showing you a little bit of math notation. I mean, it's good to kind of, I'm not going to like force you to just memorize all this, but just by using it contextually, you'll kind of get a feel for this.
What's that mean?
So that means if C is an element of, and then a capital script R, that's our symbol for the set of real numbers. Okay? So you'll see this a lot, something like this. And that's just saying that this C is just some real number. It's an element of the reals. It could be any real number. No limitations. So what do you think the limit of C over x to the R as x approaches infinity must be? Any suggestions?
So is a capital R the same as a lowercase r?
No, that just means, all this means is the set of all real numbers, all rationals and irrationals. It just means that it's one of those. It's a real number. You could also just say C is real. But I mean, this is something you'll see in college, so I want you to get a little bit used to it. What do you think the answer to that is? So I want to know what the answer to this is. If C is just some real number and R is a positive number, a positive real number,
C.
what do you think you're going to get? Let's,
Positive C plus 1, C plus
So you're
R.
gonna be like all answered. Wouldn't it be infinitely close to zero?
okay, why?
Because like no matter what C you pick, like negative 20 or 2, that x is gonna like increase a lot faster.
Okay.
Because the exponent R and then C well C won't even increase at all. So as x increases, it'll just be closer and closer to 0.
Okay, good. You have to think about this. You have to kind of think about this in terms of the behavior of a fraction, right? The top of the fraction is constant. It's just some number, right? The bottom of the fraction, though, is changing. What's going to happen as x gets really, really, really big, regardless of what that exponent is? And it might be something like if that were a 1/2, for example. Thanks. If that were a 1/2, then it would be square rooting it, and that tends to make things smaller, right? So, for example, if that were a 1/2, when x is 100, the bottom is only 10. So it's slowing down the rate at which the bottom is increasing if R is a number less than 1, right?
I thought R had to be more than
No, it has to be more than 0. It doesn't have to be more than 1. Now, if it's a number like 2 or 3, that's going to really accelerate the growth of the bottom, isn't it? If we're taking powers, integer powers of the bottom, it's going to get big in a hurry, like 10 cubes is 1,000, right? But if it's a number between 0 and 1, it's going to be taking some kind of a weird root of x, and it's gonna make it smaller, but it doesn't matter, because what's x approaching? Infinity. So it doesn't matter how slowly it grows, it's gonna grow without limit, right? Because infinity is darn big. I mean, it's big without limit, right?
So it's closer you get to infinity, the smaller it gets?
Well, no, the bigger it's gonna get, right? Now, let's take an example. Let's just say, what if r were 1/3, right? So if r were 1/3, let's just see what would happen if we had c over x to the 1/3. Let's just say that's f of x. Well, then f of 1,000 is just equal to, and let's make the c, you pick, I don't know, 4. 2, there we go. We could even make it something, what? We could even make it something big if we want to.
Like 37.
Oh, 37, okay, that's big, okay. 37, so then f of 1,000 would be 37 over the cube root of 1,000 is 10. So I just get 3.7,
Okay.
right?
But what if it was 2/3, then what?
Well, then it would be, then we'd end up with 100 on the bottom, and it'd be 0.37.
The important part is the x, that's what we're supposed to do here, the x is approaching infinity, so it's getting infinitely bigger.
It's getting bigger. So if I take another value, let's take something like, instead of that, let's take a million.
Billion.
Well, yeah, r is a constant.
F of a million is gonna be 37 over,
Yeah,
is that 100,000?
Yeah.
Million.
It's 10.
There we go. So that's gonna be 100. Whoops.
Yeah.
Yeah,
That's some good.
okay. What's happening? The bottom is getting bigger, even though it's getting bigger at a pretty slow rate, it's still getting bigger. What's happening to the overall fraction? It's getting smaller, right?
What if you
Right.
square it instead of
So as the
Say it again.
What if you square it instead of making it 1/3? The opposite?
Well, then it'd do the opposite. Then the bottom would get big in a real hurry, right? But I just want to illustrate that even if the bottom is lazy, even if it's a function that's gonna not grow very rapidly, it's still growing, and so overall, the fraction is getting smaller, right? If I use this, if I go f of a trillion, whoops. Come on,
it's not a
it's out of ink again. Yep. F of a trillion is gonna give us 37 over a million. No, is that right? Yeah,
I don't actually know. A million.
right?
What's 37 divided by a million?
It's a small number. It's getting pretty close to
Do
zero,
you
isn't it?
know for sure?
Right.
Though? I want it
I
exactly.
wonder if I did that right. 6, 18. I don't think I did. I think that's supposed to probably be a quadrillion, but it doesn't matter. You get the point. Yes.
It doesn't matter.
Wait, so if c is an element of r, what if, r is greater than 0, okay, never mind.
So it doesn't have to be. This could be. So what if this had been a negative? Because c could be anything,
Yeah.
right?
But I was thinking r was negative, but never mind.
Okay, don't get sidetracked. If c were negative, all that's going to do is make these numbers negative. Big deal. They're still approaching 0, aren't they? Right? So the answer is always 0, right?
Wow.
Because the bottom is growing without limit and the top is not. And as the bottom of a fraction gets bigger, the
number
overall
gets
fraction gets smaller.
So it's approaching 0.
Yes.
Just wondering, did you use like the European definition of a trillion? Because like a trillion for American definition is 10,000.
Do
But I
it.
think- But I think the other one.
What?
Well, like,
No.
or I mean, like for that, right? With the.
Yeah, this should have been a quadrillion, I think, probably. Or maybe even a
Well,
quintillion.
I was thinking like, like the European, like the British. and people-
How do they define a trillion?
A trillion, well, a million is 1 with 6 zeros, right? So
Yeah.
a billion is 1 with 12 zeros.
No, 9 zeros.
No, like this is how they define it.
Oh, serious? No.
Yeah, then a trillion is 1 with 18 zeros.
No. No, they can't. What goes in between?
Wait, look
That
at
doesn't make any
No,
sense.
like they just have different words for the ones in between, just like how we have like 10,000 and 100,000.
What do they have?
Ryan is.
Look it up.
What do they
I
have?
will,
for,
that's-
like,
I put-
10,000?
That can't be, because I've read
Can
lots
we
of
look
physics
it up
books that
right
are
now?
European, and they always got
Sorry,
trillions
I'm
and
looking
trillions.
it up.
That's bizarre.
It all makes sense now.
Trillions. I mean, man, so-
You just researched back that?
Okay, does that make sense though? Jolie's on the job here. She's double. She's our fact checker.
Like if the bottom is square,
That's gonna blow my mind if that's true.
it would be a different answer if it
Okay,
was
shh.
square.
Say it again. It would. Yeah. But no, it's not. The answer's always gonna be 0.
Even if the bottom is, even if R equals 2.
Doesn't matter. Doesn't matter what R is. As long as R is just some positive real number, it doesn't matter what it is. The limit as x approaches infinity will be 0. Now the rate at which it kind of gets small is going to change based on the value of R, right?
Okay.
If R were 5, it's going to get small in a hurry. Like, I mean, just to illustrate this, I don't want to belabor this too much, but what if we had g of x equals 37 over x to the 5th? Well, then g of 10 already is just 37 over 100,000.
Okay.
It's already pretty small, just doing it in a hurry. See what I'm saying? Okay.
I found a video
The
explaining
internet
it.
is saying
Really?
it's true.
It's true.
They call it 1,000 million,
Yeah.
which means like 1,000 billion, 1,000 trillion.
Wow, when did they, because they don't do that in science. When did they stop doing that? That's weird. That's, those,
Ryan-
is it British or?
Been for a
British and
while.
European.
Really?
Someone explain.
Huh.
I don't care what.
Strange.
Makes sense. So like,
It says
Million.
that it's because
Strange.
Latin is not taught to the same extent.
Hey, I got
as
it.
in Europe.
Oh, yeah.
I don't
I
know.
found a thing that
Just
said
a-
This is from Ask Dr. Math.
it says the reason for this difference is historical and relates to the fact that Latin is not taught to the same extent in America as it is in Europe. The bimillion
I've
and
heard that
trimillion
before.
is an obvious extension from 10 to the 6th and 10 to the 12th and 10 to the 18th in the European system, and these billion and trillion respectively. In America, the need for a simple word for 100 or 1,000 million and an absence of Latin led to the misappropriation of the word billion. England held out for a long time with the 10 to the 12th meaning of billion, but it was eventually overwhelmed by the sheer weight of scientific and mathematical literature that used the American interpretation. So billion in England is now used in the American sense. Europe may eventually follow suit, but it will be a change from the logical system to an arbitrary one.
So.
Of course, Britain likes to bash America, say we don't understand things.
Yeah.
I think that there really are just different arbitrary modes of defining what a number its name is.
Oh, sure.
Because they're just
I think
definitions
Britain just likes to snipe us.
5 million is different.
Well, that doesn't make sense, like, if they're gonna do it like that, like, if they're gonna make a trillion to the 18th, shouldn't the trillion be the 24th then? Since it's doubling.
No, no,
Well, for us, a trillion is 10 to the 12th, and for them it's.
No,
just
wait,
They're looking at compared to a million.
Oh, all of them are compared to.
Yeah, but just so you know, I mean, that's like if you read a physics book from Europe, it's gonna say, it's gonna use the American, in science, they use the American method for naming trillion and billion. Okay, here we go. Let's get moving though.
that's crazy.
Interesting little side note. So do this for me, please.
Numbering system figured out.
Okay. Try that. What's the answer? Anybody know?
Zero.
No.
Negative 5.
Two. Second guesses.
Okay, the answer, let's take a look at it.
Two.
We can use our properties of limits, which are probably a little rusty. We haven't done that in a while, but remember, we can take limits term by term. We can break limits up into separate limits of the terms, which makes it a little bit easier. So this looks like the limit of 5 as x approaches infinity minus the limit of 2 over x cubed as x approaches infinity. What's the limit of 5? 5. It doesn't change, right? It's a constant.
So the answer would just be 5.
Yeah, and then what's this limit here?
Zero.
That's gonna be 0, isn't it?
So it's 5. Mr. Was there something
Yeah.
limit of a constant zero?
What's that?
The limit of a constant is not zero?
No, no. No, the limit of a constant is the constant. It doesn't matter, right? Think about it this way. If we're taking the limit of the function, what does the function y equals 5 look like? It's just a straight line. It doesn't matter what x approaches, the y value is always just gonna be 5. Okay, so what we can do then, do we have to do all that nonsense? No. Here's the shorthand notation. We know that the limit, whenever I have a constant divided by any power of x, that was that last theorem we looked at. We always know that the limit is 0. So our answer is just 5.
So,
But golly,
What if it
yeah.
would have been infinity, what if it would have been like a real number?
Well, then that's a whole different concept. If it's a real number, then we'd have to plug it in and see, right? We would just use direct evaluation. Okay, so let's try another one of these then. Let's try one that's not so easy.
I was just starting to understand though, so.
Oh, you'll still
I think
understand.
if we do like 0, 1, yeah.
Let's relearn
Okay, what about that?
There you go.
No, maybe not. We don't know. We'll have to find out.
2.
Okay, this one, the answer is gonna be 2. The answer is gonna be 2, but let's see if we can see how that's gonna be the case. We don't have a theorem that works directly here, right? But what we could do, we could try something here. We can see that the biggest power of x that we have in the top or the bottom is just x to the 1. Let's factor out an x to the 1 from both of these. So that gives us, on the top, x times what? 2 minus,
1,
no.
x, 0.
Remember, if I'm factoring something out,
X
I'm,
minus 1.
no. Oh, to the minus 1, yeah. To the minus 1. When I factor something out, I am dividing it away from each term, right?
So 1.
So, yeah, 1 over x, right? Or x to the minus 1, but I want to write it as 1 over x. I want to actually write it as a fraction. You'll see why. On the bottom, if I factor an x out, what am I left with?
1 plus 1 over x.
Okay, algebraically, the x's cancel, don't they?
Yes.
Right? And we're not looking for solutions here, are we? Right? Why can't we cancel the x's here? Well, we cancel the x's because we're not looking for solutions. We just want the behavior of the function as x approaches infinity, right? So that's okay to do. Now that we get rid of the x's, what have we got here? Then it just looks like the limit of 2 minus 1 over x over 1 plus 1 over x as x approaches infinity. And do you see any parts of this limit that are going to go to 0 as x goes to infinity?
The 1 over x.
The 1 over x's do, right? So that's going to go to 0, and that's going to go to 0, giving us what result?
2.
2 over 1, which is 2.
How come we couldn't do that earlier?
Well, we just learned it.
No, I mean, earlier in the problem, like, never mind that anymore.
Right, because we had to factor the x's out first, right? Okay, let's try another one.
Sorry.
Yep.
I don't understand why you went, like, the top, how you got 2x minus 1, and then when you factor out an x, you got 2 minus 1 over x.
Because when I factor out an x, I'm undistributing it. I'm dividing it away. So what am I left with? What am I left with here? Well, really, whatever I'm left with here is what I get when I divide the first term by x.
Yep.
What I get there is when I divide the second term by x.
Yeah.
Okay.
How do you take it out of a 1 if there isn't an x in there?
Well, 1's the same as x over x, though, isn't it?
No, true.
Right, you see what I'm saying?
Yes.
So to get Does everybody see that? To get from here to here, I'm really just asking myself, if I'm factoring out an x, what am I left with if I divide that term by x? 1 over x. What am I left with here if I divide that term by x? 2. Right? Okay?
Next one.
Wait, how do you know that the 1 over x is better than
How do I know what?
that the 1 over x is better?
Because in the limit as x approaches infinity, think about what's going on here. The bottom is going to get huge, and the top is not. And so a huge denominator means a very small fraction, right? And if the bottom gets huge without limit, then the fraction has to get small without limit. Right? Make sense?
Well, then can x equal 0?
Can x equal? No, it can't.
So there's just a whole.
Well, there would be, right, there would be a hole in the function there. But I guess it could have equaled 0 here. No, it couldn't. Yeah, it could. So the original function could have, but you're right. I can't, when I factor this x out, I've created some problems for what the function looks like when we're trying to find zeros, or we're trying to, right?
Negative 1 if x is a negative 1, so there'd be a
Right. Well, in the actual function, there is a hole at -1.
There's one at the.
It's just how.
Right.
I just.
They're just, and I guess there is here too. But at 0, see, I mean, I don't want to confuse you with this, but like normally, can we just cancel x's if we're trying to solve? Remember, I talked about this the other day. If we're trying to solve a problem like, let's say, x squared minus x equals 4.
I was thinking 4.
Were you really? I read your mind. No, that's not even what I want to do. I want to do equals 0, how about? Yeah, equals 0. I can't just divide both sides by x, right?
No.
Because if I do that, I'm going to lose a solution. You see what I'm saying?
Oh, yeah.
We're not looking for this.
Right.
We're just looking for the.
I mean, like, sometimes people say things like, well, we could add x to the other side and get x squared equals x, and then divide both sides by x and get x equals 1, but then we lost the solution 0, right? Because 0 works also. See what I'm saying? So you can't just randomly, you can't just, be careless about canceling variables, but this is a case where you can, because all we're trying to do is see what the function does way out there, right? And so we just want to get an answer for what's the limit. We're not going to leave the function like this. For all the other calculus that we do on this function, we have to treat it the real function, right? I mean, we're going to differentiate this one, not that one, right? All this is good for is just to answer the question, what's the limit as x approaches infinity?
So before we differentiate, you know what I'm saying?
Yeah.
You have to take the limit first.
What is it?
Well, yeah, but here's the good news too. It maybe will head off some of the questions and consternation. We're not even going to have to do this. We're going to come up with some rules that allow us to skip what I'm even doing now. This is a shortcut, but we can get a shorter shortcut here in a
I
second.
got a shortcut. I thought it was 2. It was 2.
Right, and we're going to be able to look at them and tell. Yeah. Okay, how about this one?
4.
Okay, what do we think the answer is there? 2/3?
2/3.
No.
Wait, I got it figured out in my head. 2/3 plus 5.
You don't have to do any math on this. You can probably just, if you just think about this, you can probably make sense of this. What do you think? 0.
Oh.
How come?
Oh, because, x on the bottom is increasing faster than the x on the top.
It is, right? So now that's a little tricky, we don't have to rely on thinking about it that way, but it works. Both the top and the bottom are approaching infinity. Now listen to this carefully, because this is a little crazy. The top and the bottom are both approaching infinity, but the bottom is approaching infinity infinitely faster. Yeah.
Infinitely.
Right. Okay. Do you see why? Because I've got an x squared on the bottom,
Is
right?
that always gonna work? Like if the exponent on the bottom is bigger than the top, then it's
Turns
gonna
out
be
it is.
zero?
We're gonna prove this generally, but yeah, it does. It always works. Now think what happens here. Would you agree that as x gets really, really big, that 1 is not even gonna matter on the bottom,
No.
right? I mean, it's gonna be completely insignificant. On the top, the 5 is gonna be completely insignificant, right? In fact, even the 2 and the 3 become pretty insignificant, right?
It's just X.
We just, this is gonna sort of end up looking like just x divided by x squared, isn't it, in the grand scheme of things? The bottom, in other words, is increasing by a factor of x more than the top.
What if the x squared is on the top? Then it make them right?
Then, well
And
then,
it's getting infinitely bigger.
then it would get infinitely big, wouldn't it? Because the top would be the one that was dominating.
So the infinity?
Yeah, it'd be,
Yeah.
right, right.
What would it be?
Infinity.
It'd be infinity.
Whoa.
And if they're the
I thought
same.
his answer was 0.
Wait,
It
this
is.
one- and if they're
This
the-
one's 0.
If there was an X squared on the
And if they're the same, the same.
You take the ratio of the leading coefficients. Yeah. Okay, so let's prove this though. Let's do what we just did a second ago. What's the biggest power of x that shows up in the numerator or the denominator? X squared. So let's factor that out.
Batteries on the bottom.
Okay, so if we take an x squared, let's do the bottom first. If we take an x squared out of the bottom, what are we left with? Hey, listen please.
3 plus 1 over x squared.
Good.
Okay.
What about the top?
2 over X plus 5 over X squared.
Okay, so in the limit, as x approaches infinity, we can cancel those, right? In the limit, what happens? What's that do?
0.
What's that do?
0.
What's that do?
0.
Whoa.
0. 0 equals 0.
Okay?
On that note.
Wait, just a moment.
We got stuff.
See ya.
What is going on with 0? Whoa.
Okay, so let's see what happens. Let's try another one.
What are we?
Hey, we gotta get through just a little bit more so this makes sense before we end. We do one more, maybe 2 more.
This doesn't.
Okay, what about this?
0. Infinity.
Okay, but we gotta be a little bit careful. We gotta be a little bit careful here with this one. Now, look what's gonna happen when, okay, let's factor out an x cubed.
Okay.
If we factor out an x cubed, what am I left with on the top?
2 plus 5 over x.
Okay, on the bottom,
3 over
3 over
x.
X minus 2.
x cubed, okay? So then in the limit, as x approaches infinity, those cancel. What happens?
That's fine.
Infinity.
That's gonna go to 0, right? That's gonna go to 0. What's that gonna go to?
0.
It's gonna go to 0, isn't it?
Yeah, 3 over X.
Yeah, right? Goes to 0.
And so,
Where's the 2?
if it's 0,
No, it's 0.
Yeah, okay. That's
what if it
Listen,
was
please.
3 over 2?
What do you mean, if this was?
Yeah.
Yeah, like, how could it be 3 over 2 though?
Like if x equals 2.
Well, but it doesn't. X is approaching infinity, right? So this looks like 0, right?
Yeah.
Okay, but now, what kind of 0? Is it gonna be a 0 plus or a 0 minus? Now think about this. 3x is approaching positive infinity. Positive divided by positive is
The positive.
positive, right? So on the bottom, we're gonna get a 0 plus, right? This one, who cares what this one is, because this one's so much smaller. This is the one that dominates, right?
Yeah.
Okay, make sense? Watch closely.
Okay.
Okay, on the top, we're gonna get, this is just a positive 2. So our final answer looks like 2 divided by 0 plus.
Yeah.
Okay, we've done this before, right?
Positive infinity.
So that's positive infinity. When I divide by 0, I know that it's getting infinitely big, and positive divided by positive is positive.
Back to
Right.
the-
Okay, what if, let's change things slightly here. What if we had been approaching negative infinity?
It would be
Negative infinity.
0 minus.
That would have been a 0 minus, wouldn't it?
Yeah.
Right? We would have had to tweak things a little bit.
Yes.
Right?
But if it was negative infinity, it would have been all flat.
If it's negative infinity, but the same.
Yeah. Yeah, they're still big. Okay. Well, are we out of here in like a minute?
Yeah.